So usually when people try to figure out what causes a disease, they try to figure out was it genetic or is it environmental or some interaction effect. But you study these systems that are kind of in between the genes and environment. And I think you've been thinking about the different ways in which a metabolic system can fail. Can it go into a runaway feedback mode where positive feedback just takes it off the map?
Yes, it absolutely can.
Are there examples of that?
And there are several examples of that, actually, and it depends in part on what system you're looking at, because a lot of these systems are designed to stabilize certain critical reactions. Along with that comes the fact that other reactions have to compensate somehow for variation, and it is those reactions that can become destabilized.
So really critical to health are these systems that stabilize other systems.
Correct.
And if those are not working right, things go haywire.
And
I think you showed a slide today about something that was going like this until you took out the regulation system, and then it went like this.
Right. In many of these systems, we have reactions that, if they're perturbed, they can actually reverse direction. They can increase by in rate about 5 or 10-fold.
So I've seen lots of people with so-called hypoglycemia.
Okay.
There was a time when that was quite a popular thing to study, and we would give people a big glucose load, and we would see how high they went, and then how low they crashed afterwards. And I think we just try to figure out what's wrong with these people. Do they have hypoglycemia or not? But I think you're kind of thinking about the system that stabilizes glucose might give us new insights into what's going on there.
Well, I think it's absolutely critical to really understand the mechanism. The overall effect, hypoglycemia or hyperglycemia, is horribly important. But what you really want to understand is why it is that it undershot, for instance, after having overshot.
So could you, with your mathematical model of blood sugar regulation, make predictions about which aspects of the system would make a person vulnerable to becoming hypoglycemic after a glucose load?
Yeah, absolutely.
And then you could get actually looking for the alleles and genes and see if you're right.
Yeah, the reason we can do that, absolutely, and the reason we can do that is because we've
got a model.
We have a model that has all the components of the system in it, and we can turn each of them on or off.
So has anybody done that? Taken a population of 100 people who have hypoglycemia and seeing if your model is validated by their results?
We've done it the other way around. We have seen if our model can actually reproduce the results obtained in human populations.
It's more challenging, I think, to start with the clinical population and see if you're right.
Well, but that's what we've done. So we've started with a distribution of a population and see if our model can reproduce that. But what we can't do is to change, is to interfere with the human population. There are ethical reasons why we can't do that.
But can you take people at this end of the distribution who are particularly prone to hypoglycemia and say, I predict these people have these different alleles, and then go and see if they do?
We can have a population in our mathematical model that replicates those individuals with hyperglycemia. Then we can go into the model and see what were all the factors that predisposed them. And then we can ask questions, well, do those factors correspond to factors that we can actually measure?
So do you teach medical students at all?
I teach pre-medical students.
Does it do any good for doctors to learn about evolutionary biology, or is it kind of irrelevant for them?
Well, I think it's terribly relevant, and I certainly teach it to my pre-medical students.
What good does it do, and why do you think it's useful?
Several reasons. One of the things that you do in evolutionary biology is you have to come face to face with variation. And
people don't like variation. They like there to be an ideal type, a normal genome, a normal personality, a normal body.
And there is no ideal type.
There's no such thing.
There's
no normal genome.
There's no single type.
It's a very hard idea for people.
And it has to be important for doctors to understand that no two individuals are alike.
Yeah.
In particular.
So that's one really big one.
Then the other aspect is we would like to know what the origins of a lot of diseases are. Why it is that we accumulate diseases as we get older. That often has to do with the fact that there's been no selection against the ability to survive old age diseases because you're past your reproductive age. So simply
and what about the possibility that some things give you an advantage earlier but a disadvantage later?
That's a possibility, and you would have to know those specific examples of that. The general idea that we did not originate fully formed humans, but we had to come from somewhere, and that we are all carrying an enormous amount of baggage of our ancestry, it has to be important. It has to do with the kind of mutations that we have. It has to do with the fact that we live in environments that are very often hostile to ourselves. The one thing that we have not talked about at all is this idea of match and mismatch. In other words, that we now live in an environment that is not the one that we evolved in.
Right.
And an awful lot of our diseases are because we are not really well adapted to our modern human environment.
So there's a general principle that I teach, and I'm going to ask you whether I'm saying the right thing to my students. It was based really on Ken Weiss and his idea about that if you find a common genetic variation that has a strong effect on a disease that influences fitness, it probably is actually a gene that didn't do much harm at all in the ancestral environment. It's only because it's interacting with something in modern environments that it has an effect.
That's distinct.
So a lot of these genes that influence heart disease and breast cancer and the like, they're not genes for breast cancer, heart disease. They're genes that interact with something in the modern environment to make us sick.
No,
Does that make sense?
That's excellent reason for believing that an awful lot of that is going on.
But the profoundness of this for medical students and everybody really is, if you find a common gene that has a big effect on health, it probably reflects something in environment, not something that's a genetic defect.
Yes, because the properties of a gene are not a property of the gene. Again, we know what genes do. They code for proteins. The effect that a gene has on a trait or a disease is not a property of the gene itself, but it's a property of the system in which that gene operates.
There's no such thing as a good gene or a bad gene, except, well, there are bad genes, but there's no such thing as a good gene or bad gene, except in an environment interacting.
Except in the context in which that gene acts. And if that context changes, because our environment changes, the effect of the gene will be different. Yeah.
I mean, for instance, a lot of us have ApoE4, which is a gene that makes you more vulnerable to atherosclerosis and stroke and Alzheimer's disease. But it turns out it may also provide protection against infection. And like now we're to this general theme of trade-offs, up, down, and all around.
And an awful lot of the mutations that persist in human populations also do so because there are trade-offs. Yeah. They're good for one thing, but that makes their presence bad for something else. Right. And those are widespread and also quite common and increasingly being discovered.
So Fred, we're so glad you joined us here today. I think we have a whole bunch of segments that people are going to appreciate watching. Any last words for the audience about why studying mathematical models and metabolism is so fascinating?
Well, first of all, delighted to have been here. And I think that the main take-home message, for me at least, in studying mathematical models, is that it brings you face to face with all the assumptions that you make about a system. In order to make a mathematical model, you have to be completely explicit about what you believe or how you believe the system works.
No hand waving.
No hand waving.
No words like very
parts.
or not so much.
And if the mathematical model doesn't work, it isn't because the mathematical model was bad.
Okay.
It is because your understanding of the system was incomplete.
Forces you to say what you really mean.
Correct. And there is no more accurate way of coming face to face with all the underlying assumptions that you make about a system.
Wonderful. Thank you so much for being with us.
You're welcome.